Good morning. Very happy to be here. Thanks for having me. Um, I actually I took this summer school almost 20 years ago, and it was a really great summer. And I got to know the speakers, and it was a fantastic experience. So I'm really happy to be here and pay it forward. What I'll be talking about today will dovetail nicely with, hopefully, with what Mike was talking about yesterday. But I'm going to start from the very beginning, sort of from scratch. So my notation is going to be this. X is going to be the set of alternatives. These are the things that the agent or subject in an experiment is choosing between. The agent is choosing from a choice set, which I will call a menu. So this is a subset, a finite subset of capital X. And the main sort of object of interest is going to be the probability with which X is chosen from A. So that's rho X of A, and rho is going to be called the stochastic choice function. The main model that I'll tell you about is something that you already know about. I'll just sort of take it in slightly different directions that you know about. But I call it the Bayesian expected utility model. And it nests as special cases some of the things that Mike talked about, like choice between low-up trees, perception of numbers. But it has many, many other applications. And it's basically the model in economics. And you can think of it as sort of the rational model. So it's going to be a useful benchmark for this school. It has three words in its description. Bayesian expected utility. So utility is something that the agent is maximizing. The utility has an expected form. It's not any particular utility, but expected utility. And the expectation is formed using the Bayes rule. So I'll spend roughly a third of the first lecture talking about each of these components and what do they mean for choice. Okay, so what does it mean to maximize utility? You all know, but I just want to establish some notation so that we're all on the same page. So utility of item X is U of X, it's a number. Utility function is a mapping from X to real numbers. Our analyst or experimenter will observe the agent across a variety of choice contexts, variety of menus. So script M is the collection of menus observed in the experiment. And the choice function is a mapping from menus to choices, such that for each menu, the choice from that menu belongs to the menu. So the menu is like a budget set. What you choose, you have to afford what you choose. Okay, that's the only constraint on the choice function. But we won't be interested in all choice functions. Predominantly, we'll be interested in choice functions that are represented by a utility function. So these are the sort of the rational choice functions. A choice function is represented by a utility function if the following is satisfied. For any menu, the choice from that menu maximizes the utility function. So U of X is the maximal utility you can attain over the menu. Any questions at this point? Good. So the revealed preference theory is sort of asking what are the kinds of choice functions that can be rationalized by utility maximization, that can be represented. And the key assumption in all of this is the utility function does not depend on the menu. Your utility is not affected by what is available to you. It's something that you enter with into the choice problem. Okay, if you make utility dependent on the menu, anything goes. Any choice function can be rationalized. So that's not a very interesting model. Okay, so what's the answer to the question? The axiom, it's called Sen's alpha axiom. It has many other names. IIA, independent of irrelevant alternatives, says that if you have two menus that are nested, A and B, A is smaller than B, and X was chosen from B, then X must be also chosen from A. And the proposition that you all learned in your first year course, hopefully, says that for a finite set of alternatives, and if the collection of menus contains all pairs and triples, this alpha axiom is equivalent to utility maximization. So if the choice function satisfies the alpha axiom, then there must exist a utility function that represents it, and vice versa. If the utility function, there is a utility function that represents a choice function, that choice function must satisfy the alpha axiom. Just a very brief proof of necessity, just so that we are all awake. Suppose that utility function does represent a choice function chi, and that item X belongs to menu A, and menu A is a subset of menu B. Suppose that X was chosen from B. What does that mean in terms of utility? That means that utility of X is bigger than the utility of any item Y that belongs to B. But any item that belongs to B also, any item that belongs to A also belongs to B. So it must be that the utility of X is bigger than the utility of any item that belongs to A. Because all of those items were included in B. So it must be that X is chosen from A.
There's a small problem with indifferences because
Good.
you say that the choice function picks a utility.
Excellent. So I would encourage everyone not to think about indifference today. But to answer your question, Eric, the theorem is correct as stated, because actually this precludes indifference. So the way I define
I see. Okay. It's
this must be
you must have.
if you have an indifference, then this is not, well, the choice is not.
Then it wouldn't be a choice function.
It would be a choice
anymore.
correspondence.
Right.
And so, yeah. Okay, but indifference is just my viewpoint is that they just cause headaches technically, and they don't add anything conceptually. So, sorry, Eric, but yeah.
No, I do the same thing. Rule out indifference.
Okay. Sufficiency, so the sort of more interesting part of this theorem also has an easy proof, but I'm assuming that you're all awake now, so I'm going to skip that proof. You all did it as a homework maybe, or in class. Okay, so just some sort of philosophical comments. The choice function is our primitive. That's what the analyst, the experimenter observes in the lab. The utility function is something that we don't observe. This is something that is our representation. This is sort of mathematical object that is a sort of as-if object. We don't claim that the agent actually maximizes a utility function, solve some mathematical problem with a calculator or in their head. We just claim that the agent behaves as if they maximize the utility function. So an analogy that I like is with physical objects, if I let this clicker go, it's gonna fall, and it's gonna behave as if it minimizes the distance to the center of Earth. But the clicker doesn't know how to maybe the clicker has some computer in it. So, but this marker doesn't know how to maximize anything, but it behaves as if it does. Now, this is a summer school in cognition, so maybe this is not a very good philosophical viewpoint. And so maybe other speakers will talk about, which parts of the brain maximizes. But, from the point of view of theory, it doesn't really matter. And the standard view in theory is that we shouldn't really worry about this. If the theory matches the data, we don't have to think very deeply how it happens that people maximize. They just behave as if they do. Okay, so this is sort of the thing that you learned in your first year classes, but this is deterministic choice, and as Mike was discussing yesterday, a lot of choices that we observe are stochastic. So this is well documented for perceptual choices. If I give you two objects that are similar in weight, sometimes you're going to think the one in the left hand is heavier, sometimes you're going to think that the one in the right hand is heavier. So your responses will be different each time I query you. And that's why my main character there in the first slide was a stochastic choice function. It recorded the frequency with which you chose the left object and the right object. This is also well documented for economic choices, for example, lotteries. And so if we want to have a theory of this, we need to adapt our first year micro theory to stochastic choice. So we need to change our primitive and we need to change our representation. So the primitive is the stochastic choice function. So let delta x be the set of all probability distributions over x. A stochastic choice function is a mapping from menus to probabilities over x, such that the probability that something from the menu will be chosen is 1. So you can't choose anything outside of the menu. That's the same requirement as before. It's just now probabilistic. I don't insist that you choose the same thing all the time, but whatever you choose, that has to sum up to 1.
Why is the probability the right object to look at for us? Because the probability means that you've done the experiment many times. So, for example, there's time involved because it is, let's say, trials.
Yes.
So why shouldn't it be some more complicated object, like including history?
Yeah, maybe.
The probability of a single choice.
Yes, it could. So it could be a more complicated object, and we will actually talk about some more complicated objects in the second lecture. But it's better to start with simple objects first to understand them, and then maybe we can enlarge our theory. Does that make sense? Of course, yeah, the order of things may matter. But so what I'm gonna sort of implicitly assume here is that we ran this experiment on the same agent infinitely many times. So we've collected the empirical frequencies, and they have converged by the law of large numbers to some true underlying probability, and that's what I'm dealing with. So in the language sort of econometrics, I've abstracted from the statistical inference problem, and I'm just focusing on the identification problem now. So I'm dealing with the limiting frequencies here as a theorist. So I have a very good experimenter that I hired, and they did all that work for me.
But you are making an assumption here that the probability only depends on what the menu is on this occasion.
Yes.
For example, it could depend on what menu you were presented with earlier.
It could, yes, and I will allow for that later. But as the first pass, I want to have the simplest theory possible. So there are two interpretations of this object in the literature. One is that this is a single agent that I tortured infinitely many times in my lab. But this could also be a between subject experiment where I'm comparing different groups of people, and this is the fraction of subjects that chose X. The theory is actually the same for both interpretations. Yeah.
One has to, in the second interpretation, is it that one has to that is super homogeneous because you might have very different subjects in different groups?
We don't. You'll see that on the next slide. Any other questions? Okay, so that was the primitive. Now what is the representation? The main representation that I'll be dealing with today is random utility representation. So there's some random utility function. You can think of it as a probability distribution over utility functions or over preferences. So mathematically, there's some probability space, and the utility function is a mapping from omega to utility functions. When does a random utility represent a stochastic choice function if the probability of x being chosen from A equals the probability that the agent finds it optimal to choose x from A. So on different occasions, the agent will draw different utility functions. Different omegas will be drawn. For some of them, x will be chosen. From some of them, y will be chosen, and so on. And the empirical frequency of x being chosen from A matches with the theoretical probability that the agent draws a utility function that maximizes such that x maximizes that utility function over A. Omega is the probability space on which sort of the randomness lives. Yeah. There are some. I won't be talking about it today, but there are some identification results in the literature. So in the deterministic version of the model, I did not talk about it, but there is no identification of the utility function because I can always, cube the utility function. It's going to represent the same preference. Actually, any increasing transformation of utility will represent the same choices. In the stochastic choice version of the model, it's kind of even weaker, but there are some properties. I actually wrote a book about all of this, and it's on my website, and it does contain those results. Yeah. Up to more than that. So in words, what you can identify is the probability that x is the first ranked item, the probability that it's second ranked item, and so on. For each of the items, you can identify that. But you can't identify the correlations between items and their rankings. That is up in the air, and that's not identified in this version of the model. There is a version of the model in the second part of the talk with expected utility that you can identify everything. So
you assume throughout that A is a discrete set?
yes, A is always going to be a finite set. You are choosing between 2 lotteries, 3 lotteries, 4 lotteries. These are not even lotteries yet. These are just items that don't have internal structure. But it's not a, yeah. So in econometrics, this is called discrete choice theory because the choice set is discrete. Okay, and in the deterministic version of the model, our key assumption was that the utility function does not depend on the menu. The counterpart of this here is that this probability distribution over utilities does not depend on the menu. No, it could be included in the menu. The default option, the status quo, that could be one of the alternatives. It just then has to be present in every menu, but yeah. Okay, and the main question, to a decision theorist is what are the axioms now on rho such that a random utility represents rho? So the main axiom is called regularity, and it says that it's a sort of stochastic version of the alpha axiom. It says that if you have an item x in menu A, which is a subset of menu B, then the probability that x is chosen from A must be bigger than the probability that x is chosen from B. So intuitively, if you add stuff to the menu, you have to make room for that stuff by lowering the choice probabilities of existing items. If rho is deterministic, that is exactly the alpha axiom, but it also holds for for stochastic choice functions. And you can see easily that any random utility representation must satisfy regularity. So define the set n of xa to be the event in which the agent finds it optimal to choose x from A. We already discussed a second ago that if x it maximizes u on B, then it must maximize u on A. So that means in the language of these n sets, it must mean that n of xa is a superset of n of xb. So it contains more utility functions than n of xb. Because, I don't care now what these utility functions do outside of A. So if it's a bigger set, it must have a larger probability. That's the proof. Okay, so the sort of regularity axiom is a necessary condition. Here's some classic examples of violations of the alpha axiom. So choice overload is one. That's the one with a sort of status quo option. So it's an experiment where you have two treatments. There is a tasting booth set up in a supermarket. One has 6 varieties of jam. Another one has 24 varieties of jam. And the observation is that in the 6 varieties, 70% people chose the default option of not buying any jam. But if you add more varieties, the percentage of people who choose that option goes up as opposed to going down. Interpretation being people get overwhelmed by choice and they just don't make any choice. Okay, so that's not allowed by random utility. Another thing that's not allowed by random utility is another sort of classic behavioral marketing experiment, asymmetric dominance or decoy effect. So you have these two options, x and y. They live on some dimensions. They have some attributes to them, and you like both of these attributes. If you add a third option that is dominated by y, makes y look more attractive, the probability of y goes up. Violation of regularity. So as you see, this is a sort of between subjects. Actually, I didn't say that explicitly, but this is a between subjects experiment. But the sort of the math, the theory is the same. Any questions about this? So I'm ruling all of this out. Now, I said that regularity is necessary for random utility. It actually is sufficient if there are 3 elements in the grand set of alternatives. Not going to prove it to you, but basically one way to think about it is that these n sets, for any fixed menu, the n sets form a partition of omega, because some utility functions will choose x, some utility functions will choose y, some utility functions will choose z, and so the set of all utility functions gets partitioned by these n sets. And we have as many, and the stochastic choice function defines a probability distribution on the cells of this partition. It tells us the probabilities with which these utility functions occur. And when I change the menu, I'm changing this partition. So now I have as many partitions as there are menus. And what the axiom has to make sure is that these probability distributions on these cells are consistent with one underlying probability over the whole omega. And that's what regularity does exactly. But as soon as you have more elements in the choice set, regularity by itself is not strong enough to ensure that these probability distributions on these different cells or these different partitions are consistent with each other. And you need to add more axioms. I find it hard to intuit what these axioms actually mean. I will show this axiom to you, but only briefly. Then I'm going to switch gears and talk about lotteries. There, the axioms are much nicer, and I'll spend time talking about those. But in the abstract version of the model, the axiom looks like this. So I am basically summing over supersets of A the choice probabilities of a fixed alternative with these alternating signs, and this sum has to be positive, not negative. That's what the axiom says. You know, you could, if you sit down and think about it, it does make sense why this is necessary. I'm not going to try to convince you of that today. It's actually, yeah, so it's necessary. It's also sufficient. That's even harder to convince yourself. But it's true. Yes, so you could spend a good chunk of time on this. I'm not going to do that.
Morally, should one think of this as some kind of smoothness of the
No, because everything is discrete. So it's really a combinatorial axiom. It's sort of like an inclusion-exclusion formula. It actually literally is a version of sort of more abstract version of the inclusion-exclusion formula in graph theory. Okay. So a couple of other representations. Eric?
So that axiom I find not easy to penetrate, but you could imagine something stronger, which is no longer necessary, but might be sufficient.
Mm-hmm.
And I would have thought that you could give some nice sufficient conditions along with regularity. Is that not possible?
It may be.
Oh,
Yeah.
but it's not been explored.
Not that I know of. Not that I know of. We sort of have an obsession in my crowd that this following or equivalent is really a holy grail. It's really good if it is. It's really, really good. Okay, so before I add lotteries, I just want to talk about a couple of other representations that you see out there. So one that you see in econometrics a lot is called additive random utility. And here the utility function is deterministic. I'm going to call it V. But there is a random shock that each alternative gets sort of shocked with. And this random shock has a density and full support. And rho has an additive random utility representation. If it has a random utility representation with this form, u of x is equal to v of x plus epsilon of x. And now v is deterministic, epsilon is random, is stochastic. Some special cases that you saw in your first year metrics classes are logit, where epsilon is IID over alternatives and has this type 1 extreme value distribution. Type 1 extreme value. Another thing that you saw is probit, where epsilon has a normal distribution. So these are all special cases of additive random utility, and additive random utility is itself a special case of random utility. You might ask what special case it is. It actually is not a very special case. It is pretty much equivalent to random utility. It's just a way of rewriting random utility. The only thing that has bite is this assumption that epsilon has a positive density and full support. And so what this buys us is an axiom that's called positivity, and it just says that each item gets chosen with a positive probability. So that's a convenient thing to have when you estimate things, like econometricians like to, because if something has 0 probability, and in your data you see that it was chosen, that's that refutes your model, you can't estimate that model at all. The likelihood function is degenerate. It also, this axiom cannot really be rejected in any finite data set, because if you didn't see something chosen, maybe you didn't make enough observations. Maybe the choice probability is very, very small but positive.
Any row with full support can be represented by an adequate random filters?
No, I'm saying that any row, so this proposition is saying any row with that satisfies positivity and random utility can be represented by additive random utility. Was that your question? Yeah. So this way, this sort of econometrics way of writing things doesn't really do anything except for positivity, as long as I don't put any assumptions on epsilon. Of course, if I put assumptions on epsilon, like those two, then I am making assumptions. In fact, even if I just make the IID assumption, that already ties my hands a lot in terms of what kinds of rows I'm talking about. And there are all sorts of paradoxes in econometrics that you've learned maybe about that have to do with this IID assumption, like the red bus, blue bus example. I'm not going to talk about that, but these are all consequences of the IID assumption. Okay, so that's additive random utility. Yet other kind of animal is what's called the loose model, the loose representation. Rho has a loose representation if there exists some function, kind of like a utility function, but not really, because it's allowed to take only strictly positive values. And the choice probability of x is proportional to W of x. That's what Luce decided to, this is his model. And what's the interpretation? So one interpretation is sort of, I don't really know what this means, but W is sort of the response strength, and choice is proportional to that. A sort of more mathematical way to think about this model is that the loose representation is really like a conditional probability. The probability, there's some probability distribution on the grand set X, and if you look at the probability distribution over A, it's just a conditional of that on A. So that's a very specific stochastic choice function. A general stochastic choice function doesn't have to have this property. You can rewrite this model as something that maybe you've seen more. It's sometimes called the softmax model, just by taking logs of W and rewriting it this way. The choice probability of x from A is e to the v of A divided, sort of normalized, where v of A is now sort of like a deterministic utility function. It's not essential, so there are ways to relax that assumption, but Luce actually did talk about it, and since then there has been a thread of the literature that talks about that. But for the softmax, it has to be strictly positive, because the exponential function is strictly positive. You can't do anything about that. Okay, so what is the axiom behind Luce's model? There actually is a pretty simple axiom that Luce called the independence of irrelevant alternatives, but we already have an axiom that's called the independence of irrelevant alternatives, so I call this Luce's IIA. What does Luce's IIA say? It says basically that if I look at two items, the ratio of their choice probabilities does not depend on what else is in the choice set. And that axiom characterizes the Luce model, and moreover, the Luce model is equivalent to the logit representation. And that maybe you've sort of, if you've seen logit enough, you know that logit is equivalent to softmax. So maybe that's not very surprising. Any questions about this?
This seems to be an example of what I was asking for before. This is a stronger axiom than
Oh.
and it is sufficient to get a close function. In fact, it gets you more than
Yes, so I guess I didn't really parse your question back then. So yes, so let's take your question again. So if you have an axiom that's sufficient but not necessary, that necessarily means that you're going to carve out some choice functions, and in this case you're carving out those loose choice functions. Yeah. Okay, so now that I understand your question, here's an example, Eric. So yes, there have been other ones as well that carve out very specific.
This is pretty easy to understand.
This is pretty easy to understand, but it's a very tiny sliver that we're carving out, and it's sort of the most prominent model of stochastic choice. That's why I'm covering it, but it has a lot of problems, including the red bus and blue bus and other sort of paradoxes. Okay, so far, just to summarize what we've covered, random utility is equivalent to regularity plus these ugly things. Random utility plus positivity is equivalent to additive random utility. Additive random utility plus IID plus type 1 extreme value is the same thing as logit, is the same thing as loose, and is equivalent to positivity plus loose's IIA axiom. You might ask, what about additive random utility plus IID without any functional form assumption? Do we have an axiom for that? No. Open question. Okay. So Bayesian expected utility, we've covered utility. You could spend a lot more time on that, but we're going to move on, and now we're going to talk about the expected part. So now the agent is going to be choosing between lotteries. So X is now delta of Z. It's the set of probability distributions over some set Z of prizes. The typical items of X are now called P, Q, R. These are lotteries. And I will specify utility to have an expected utility form. So U of P is going to be the sum over Z, little u of Z, P of Z. So P of Z is the probability that lottery P assigns to outcome Z. And U of Z is a sort of a new thing. It's called the Bernoulli utility function of Z. And you've studied that in your first year classes as well. And you know that when Z is money, then concavity of U corresponds to risk aversion. And the more concave U is, little u, the more risk averse the agent is. The key thing about expected utility is that it's linear in probability. So what does that mean? Suppose I have two lotteries. I will define now a new lottery, a sort of mixed lottery. So for any probability alpha, I will define a lottery alpha p plus 1 minus alpha q. What is that lottery? That lottery attaches to prize z. It attaches the probability alpha p of z plus 1 minus alpha q of z. You can think of this as a compound lottery, where you toss a coin with probability alpha gives us heads, with probability 1 minus alpha gives us tails. If heads come up, I'm going to play P. If tails come up, I'm going to play Q. This is actually not a compound lottery. This is a one-shot lottery where I've reduced this compound lottery already for you. And you already know that, capital U has an expected utility form if and only if it is linear in, there's a typo. There should be a, no, there isn't a typo. If it's linear in probabilities. So U of the mixed lottery is the weighted average of U's. This is a very powerful property of expected utility that gets exploited a lot in the von Neumann-Morgenstern theorem, where the key axiom is independence. And we'll see its version in the stochastic choice world. So what's a random expected utility representation? I will say rho has rho now is a stochastic choice function between lotteries. It has a random expected utility representation if it has a random utility representation where with probability 1, the utility function takes a expected utility form. So you can think of this as there being some probability distribution over these Bernoulli utility functions. So maybe the agent's risk aversion is not stable from one choice situation to another, and every time they choose, the coefficient of risk aversion gets drawn, and they choose according to that. Or I'm studying a between subjects experiment where different people have different risk aversions. And now I have the probability over these coefficients corresponds to the sort of empirical frequency of risk aversion in my subject pool.
This is a representation. I think the wording here is misleading, where with probability 1 all here are that representation. So there could be something that the utility aren't necessarily expected utility, but there could still be on the aggregate representation that is.
Okay, so you are saying that there could be many representations, and some of them of the same row. One of them is of this form, and another of them, for each utility, for each capital U, I cube that capital U. And then it's going to represent the same preference over lotteries, utility by utility, but the cube of capital U does not have an expected utility form because it's not linear in probabilities anymore. Is that what you're referring to? Yeah. So I'm just defining what a random expected utility representation is, that there could be other representations of the same choice. I'm silent about that. But I'll restrict attention to those. So what are the axioms behind what are the axioms behind random expected utility? What is the stochastic choice version of the von Neumann theorem, von Neumann-Morgenstern theorem? So I have choice from menus, so I need to develop a little bit of a terminology for what it means to mix menus. So I will mix menu A with lottery Q with a fixed proportion alpha. And that new menu is just the menu of all mixtures between things in P and that fixed lottery Q. So lottery by lottery, I take a lottery out of the menu, I mix it with Q, put it aside, and I collect all of these things. That's a new menu of mixed lotteries. And the main axiom says that the probability that lottery P was chosen from menu A is the same as the probability that a mixture of P and Q gets chosen from this mixed menu. And you can see kind of why this axiom must be necessary if we have a random expected utility representation. It's necessary because basically these n sets are linear in probability. So if little u belongs to n of PA, then it also must belong to n of alpha p plus 1 minus alpha q and the mixed menu. Because, basically because of this. Okay, any questions before parsing this still? So here is something that doesn't satisfy this this axiom. So this is the LA paradox, or actually this is an easy version of the LA paradox, which is called the common ratio paradox of Kahneman and Tversky. So I have two lotteries, P and R. That's one menu, and I ask you to choose P and R. P gives $4,000 with probability 80%, and 0 otherwise. R gives $3,000 for sure. And the other menu is P prime R prime. So P prime gives $4,000 with probability 20%. R prime gives $3,000 with probability 25%. Now, if you kind of look at this, this is exactly the kind of situation in which the axiom should apply, because P prime is a mixture of P and a point mass on 0, and R prime is a mixture of R and a point mass on 0. And both of these mixtures are with the same proportion, a quarter on the lottery, 3/4 on 0. So the axiom says the fraction of people who chose P should be the same as the fraction of people who chose P prime. But as Kahneman and Tversky and Allais and others discussed, this is not true in practice. In practice, people find this lottery very appealing. But once you mix this with 0, then the $4,000 is bigger than $3,000. These two probabilities are similar, so a lot of people switch to P prime. Okay, so random expected utility excludes that. There's another axiom behind this theory, which is the extremeness axiom. So I can think of lotteries geometrically as living in some multidimensional space. If there are 3 outcomes, then I can think of them as living on a plane, actually living in a triangle. And so suppose my menu is those 6 lotteries, these 5 points, and the point in the middle. The extremeness axiom says that the point in the middle will never get chosen. Why is that? Because the indifference curves of a von Neumann-Morgenstern utility function are linear and parallel. So something that's linear and parallel will never get maximized in the interior of the set. It's always going to be on the face of the set. It's always going to be an extreme point, or actually more precisely an exposed point. But I'll gloss over that distinction. So there's a whole other set of experiments that prove that this axiom is also not satisfied by human subjects. But I won't show any of them, but people tend to like midpoints. Okay, so here's the theorem. It's a very nice theorem, very difficult theorem, that says ρ has a random expected utility representation if it satisfies regularity, extremeness, linearity, and a continuity axiom that I'm not going to cover. That's why I put a little dagger on it, and a dagger on the theorem, because the theorem is not complete as stated. Okay. Any questions?
Does that continuity axiom play the same role that continuity and quantum remote constraint does?
Yeah. Yeah. Mm-hmm.
So you would get an approximation.
You would get, there are these like lexicographic probabilities or these kind of things. They would crop up here as well. That's my conjecture. I actually don't. There is no, for the deterministic version, there are papers that say what happens if you don't assume continuity. Here, I don't. This is just my speculation. But yeah, something like that would happen. Yep. By Choquet theorem, you mean the theorem from convex analysis?
Yeah, the convex.
I mean, there is a lot of convex analysis behind the proof. Not necessarily the Choquet theorem, I think. But yeah, you had a question too.
Yeah, just had a question like back on the random effect.
Uh-huh.
The next one. Hi. So you mentioned that you might have a subject with unstable risk aversion,
Mm-hmm.
and so you need more than one Bernoulli utility function.
Yep. Yep.
So here it would be for some, or if there was just one utility.
So each of the capital U's in the support of P of the script of the math fold P, the probability that governs the whole thing, has this form.
And that's unique for a
So
subject. But
so
the small u's can vary.
say that again.
So the big U is unique for a certain subject, but the Bernoulli, the small U, can vary because, as you mentioned, the risk aversion coefficient.
Well, no. So the big U and the little U are sort of tied one to one, because
Yeah.
the little U is the big U of a probability of a point mass on Z.
So
There'll be lots of big U's that will work because you can just one and a half hundred transformations.
Right, but if you normalize, so you just need to make two normalizations, and then you kill these affine transformations because there's the slope and the intercept. So if you normalize, you fix some price, and you say all of the Bernoulli utilities have to assign utility 0 to that price. That's one normalization, and then make another normalization that all of the Bernoulli utility functions, let's say they have to sum up to something, to 1. Then there is a uniqueness part of this theorem, which I actually didn't state, but I should have, that says the probability distribution over these normalized Bernoulli utility functions is unique. You can uniquely pin it down.
in that case, the risk aversion would be stable. As well.
No, it would stable.
I mean, so a single individual would have the same coefficient of risk aversion across.
They would have the same distribution over coefficients. Does that make sense? Suppose we're only looking at the within subject experiments, then they would still be variability of choice from trial to trial, but the distribution would be the same.
So there's no fixed risk aversion coefficient for a single.
No. At least in the sort of, if you interpret this as within subject experiments. If you think of rho as between subject experiments, so one subject only chooses from one menu, then their preferences may be stable. Now this probability distribution is the population frequency.
Okay, you think of it.
Yeah.
Yeah, it's just that in the random utility model, you have a fixed coefficient of risk aversion, right? Because the D is deterministic.
In the additive random utility
Yeah.
model. Yeah, let's talk about. So I'll talk about the expected utility version of additive random utility very shortly. So maybe let's get back to your question then. Yeah. Yes. Good. Okay. Okay, so let's do this other thing, this additive random utility with expected utility. So what I discussed is model 1. So let's make it slightly more specific. That let's restrict to some functional form. Let's say CARA or CRRA. Let's fix that, and let's say all capital U's have to belong to that class, and now we just have a one-dimensional family with parameter theta that measures risk aversion. Higher theta is more risk aversion. Then, okay, so for the non-economists, CARA is U of Z equals minus X minus theta Z. And the words CARA is constant absolute risk aversion. And it basically says, if I give you $1 million, your risk attitudes towards incremental wealth are the same. And CRRA is basically, log is one member of that class. It's the same thing but multiplicative. So constant relative risk aversion. So let's suppose we're in that class. Then what does random expected utility means? That means that there's probability distribution over this theta. So I can write this down as fixed theta plus some shock to theta, shock epsilon to theta. That's this instability of risk aversion. That's how it manifests here. But there's a sort of additive random utility version of this model where I add epsilon not to the parameter of risk aversion, but to the evaluation of the lottery. So I add it here. There's an epsilon of P. And that's a very different model, it turns out. There's no longer an equivalence between model 1 and model 2. In particular, in model 2, preferences over lotteries are not expected utility anymore. If these epsilons are drawn IID, then these preferences over lotteries are very wild because epsilon of P and epsilon of Q have nothing to do with each other. They don't know what P and Q are. Maybe P is much better than Q. It could still be that epsilon of P is much lower than epsilon of Q if they're drawn independently. And so in experimental economics, a lot of people operationalize stochastic choice between lotteries this way. And I just want to convince you that this is a very different model than random expected utility. It's actually not an expected utility model. This is the model that Mike alluded to in his first lecture. And so I want to push this a little further. So I think that the first model, random expected utility, has very intuitive properties. So suppose P first order stochastically dominates Q, then the probability that P gets chosen over Q is 1, according to random expected utility and CARA. Because all CARA functions are increasing functions. So P is better than Q according to any expected utility. If P second order stochastically dominates Q, then the probability, P may not be chosen with probability 1 because maybe there are some risk-loving agents in my pool, or maybe my single agent in the other interpretation sometimes is risk-loving. But if I increase theta, the probability that P gets chosen goes up because the probability that the agent becomes risk-loving gets smaller if I push theta up for a fixed distribution over epsilon. But the second model, the sort of experimental economics model, doesn't have these properties. So the probability that P gets chosen over Q does not have to be 1, because as I just discussed, it could be that P gets a very low draw of epsilon and Q gets a very high draw of epsilon and Q gets chosen on that trial. And moreover, sort of more interestingly and damagingly to this model, if P is second order better than Q, so it has less risk than Q, it could be that the probability that it gets chosen is actually decreasing in theta for high values of theta. So if I think of sort of theta, so theta is some sort of my representative agent or something like that, I drive their risk aversion up, and the model behaves in the opposite way. The probability that the better lottery gets chosen goes down.
To connect with my next matrix, can I think of model A a bit as early noise and model 1 as early noise and model 2 as late noise? So can I reinterpret model 1 as some kind of multiplicative noise on Z?
Yes. I'll talk about it a little bit. So far I didn't say when this early late didn't exist, but you can think. So far this is all late noise in a sense in Mike's terminology, but you can think of model 1 as early noise, and I'll get to that.
But then it's multiplicative on Z, very specific.
Why multiplicative?
Because there's additive noise on
Oh, in this,
theta, right?
yeah.
Could you go back to the previous
Mhm.
slide here, so I can put two models? Are there, so in model 2, there are no restrictions on the epsilon?
No, in fact, it's typically this type 1 extreme value, or a Gaussian distribution that people use in practice.
But if you impose some sorts of restrictions on the epsilons, might you then get the nice properties that model 1 has?
Well, but you would need to relax the IID assumption. So under the IID assumption, there's no, these epsilons don't really know what they get applied to, and that's what screws things up.
Is there any particular reason for assuming that?
Tractability. And the soft, you get, so you can use, absolutely not. You get to use the softmax. That's the economy of computation. No. Okay. So we've covered utility. We've covered expected utility. Now let's talk about the Bayes rule a little bit. I'm sort of building up to where Mike started, basically. So I apologize for that. You know what Bayes rule is, but I just want to establish some terminology. So there are three stages. There's an ex ante stage where the agent is facing some initial uncertainty. They have a prior belief. Then there's something that in economic theory is called the interim stage, where there's some information that arrives. The agent forms a posterior belief. And there's an ex post stage where the state is learned, so the agent knows the state. That's not a very interesting part. I will not talk about that. But just, this is ex post. Posterior is actually here, not ex post, for some reason. And the most important thing is, how does the agent form the posterior belief given their initial uncertainty and new information? They use the Bayes rule. So let's formalize this a little bit. S is the set of states of the world. These are the things that the agent has uncertainty about. The prior of the agent is a probability distribution over S. The agent has some deterministic, for simplicity, utility function. that evaluates each alternative, but the evaluation can depend on the state. That's why the agent cares about the state. In some states, you know, ice cream is better. In some states, hot tea is better, depending on weather. And so for any belief, the expected utility of x, it's just, you know, it's just expected utility of x. So I sum over all states, utility of x in that state times the probability of that state. That's my notation for expected utility of x. And the agent who's faced with menu A, ex ante, what are they going to do? They're going to choose the item that has the highest ex ante utility according to the prior. So if the utility function of the agent is deterministic, the observed choices of the agent are also deterministic. If I am somehow magically able to put the agent always in the frame of mind where they are starting with the same prior, then they're going to choose the same thing, modulo ties, which we've eliminated. The interesting thing is what happens at the interim stage. So at the interim stage, the agent gets some information, which I'm going to call a message, M in some set big M. That's maybe something that might call the noisy mental representation, or this could just be for an economic theory, this could be just a privately observed signal. And there's some signal structure, sometimes called the black hole experiment in economic theory, that is a mapping from states to probability distributions over messages. So in each state, there is a different probability distribution over messages. And because it's different, that's what allows the agent to make some inferences about the state from seeing the message. If it was the same in each state, that experiment is useless. There's no information. So for each message, there is a posterior belief that the agent has over the states. That's given by the base rule that we all love. It's just, you know, what it is. It's the conditional probability. So it's the joint probability of observing state S and message M normalized by you know, the observing of message M. So that's what QM is. Q sub M, I write it this way. And so for each message M, the agent now chooses the optimal item in the menu given their posterior QM. So there is there's a sort of informational asymmetry between the agent and the analyst now. The agent does not know the state and learns the message. The analyst knows the state but does not learn the message because the message is either a private signal or is some neuronal firing that maybe we can observe for monkeys but maybe not for humans. And so in the eyes of the agent, given a message, the choice is deterministic. But in the eyes of the analyst, the choice is stochastic. Because for each state, there is a probability distribution over messages. For each message, the agent forms a posterior, makes a choice. So there's a probability distribution over choices. Okay, what's the probability that the agent chooses X from menu A in state S? It's the probability that in state S, a message gets realized such that the posterior is such that the agent finds it optimal to choose X over everything else in the menu. And so now our primitive is a little bit richer than in the standard random utility model because now we observe, as the analyst, we observe a stochastic choice in each state. And the counterpart of the sort of invariance assumption that we had before is that the black hole experiment does not depend on the menu. It's the same It's the same signal independently of the menu. And if that's true, each of these stochastic choice functions is actually a random utility function. So if this was a little bit abstract, let's have an example. It's a character recognition task. Suppose there are two characters, either C or E, that are flashed on the screen very shortly. So maybe you don't get to see the distinction between them. There's some noise maybe. So, and the subject has to correctly identify which character was presented. So the choice set is C and E, and there are two states. The true character was C, or the true character was E, as C as E. And the utility is 1 if the agent says C and the true character was C, and likewise for E. And if they make a mistake, they get 0. Okay? They are incentivized. And because this character gets flashed very briefly, the agent doesn't see it perfectly. There's some random perception of the character. So there is a beta is a probability distribution over these random perceptions. Let's say the density of it is B. So if I want to allow here for a continuum of these random perceptions. So sometimes the agent is pretty convinced that this was a C, but sometimes they're not sure, this kind of thing. So what's their posterior belief? They enter the world with some prior over, C versus E. The posterior is now the prior likelihood, the prior ratio multiplied by the likelihood ratio. And if this is indeed their utility function, they're going to optimally say C if their posterior likelihood ratio is higher than 1. Okay? They're more convinced it's C rather than E. So that's pretty simple. Let's just massage this a little bit. So I'm going to call P the probability of C, the prior probability of C, and L the likelihood ratio. It's optimal to choose for the agent to choose C if the likelihood ratio is bigger than this prior odds ratio. Okay. So now I want to understand how often is the agent going to choose C versus E. If the true character was C. So let L of K just be the set of messages for which the likelihood ratio is high enough, is higher than K. And notice that the higher K is, the smaller the set L is. If you plug it in to the formula in my definition here, the probability that the agent chooses character C if the state is S and the prior is P is the probability of the set L of that prior ratio, and that's going to be an increasing function of the prior. So the interesting thing that I'm sort of going towards is that now the choice probability will depend on the prior, and that's something we didn't have in the random utility model. So imagine that you run this experiment in batches. In each batch of trials, the frequency of these two characters is different, and the batch is long enough that the subject gets accustomed to that frequency. Mike was talking about these kind of things yesterday. This Bayesian expected utility model predicts that the choice frequency will depend on the frequency of characters in the batch, which we can assume is the prior of the agent, or is related to the prior of the agent. So maybe we're going to throw out some initial trials in each batch, sort of call it a training phase, and look at throw out the first 1/3 of trials, look at the 2/3, then the agent sort of is accustomed to the frequency. The model makes a prediction that the higher is the probability of the character C, the higher is going to be the probability that the agent will choose C independently of what the actual character is. Yeah?
So originally in the demo, we didn't allow correlation between the services. When the first reply comes out, between subject approach, right? So
Yeah, so these were sort of the questions at the beginning. I'm sort of getting back to them. So in the beginning, there was no batches, and even if there were batches, the distribution over, utilities was invariant to these batches. But now, these batches actually mean something to the agent, and the agent is making some inferences, and that in this model, it will make a difference.
my question is, how did you raise these? I mean, in the experimental model, you show all of the time, or you exclude some of this. It seems like a similar thought process with what you're describing, having an OOD mechanical component with the design where they exclude some of the choices.
So I'm not familiar with this, and so I'm going to defer. Maybe we can talk about this over coffee. Okay, so here's how in a typical experiment it looks like. So what I'm plotting here is the probability of choosing. This is very small. I apologize. The probability of choosing character C if the true state is B, versus the probability of choosing C if the true state is C. This is sort of correct choice. This is an incorrect choice. And these different points correspond to different priors. You can see that, in a typical experiment, this is exactly how the data looks like. The higher the probability of C, the higher are both of these probabilities. And also, the harder the task is, the closer this curve is to the diagonal. The diagonal is sort of making a very uninformed choice. A perfect choice would be, here. So the model is now sensitive to both of these things, the prior and also the difficulty of the task, which I could manipulate, by changing the beta, the Blackwell experiment. And so you can see this is a much richer model than just a random utility model. Even though, as I mentioned, in each state, we have a random utility model. These are all connected to each other in interesting ways. So let's see, 10 minutes. So let's do this example as well. So now I'm choosing between two physical objects that I'm comparing their weight. So now the state is the true weight of each object, and P is the prior. M is the perception of the weight of each of these objects. There's some distribution over these perceptions. Maybe it's normal, with mean equal to the true weight and some variance. And if that's my signal structure, then the probability that the left item will be chosen is equal to phi, which is the CDF of the normal distribution, of the difference between the true weights. And so if you plot this, it's going to look exactly like Mach's sigmoid function. In psychology, this is called the psychometric function. The choice probability on the y-axis, and on the x-axis is sort of the difficulty of the task or the strength of the stimulus. You could tweak this a little bit, and instead of normal, assume that the signal equals it's still normal, but the mean is now the logarithm of the true weight. then the observed choice frequency is very similar, but now it depends on the ratio of these two weights instead of the difference between them. And that captures what in psychology is called the Weber's law that Mike alluded to. So you can create these kind of things easily using this Bayes expected utility model. Mike's model of choice between lotteries is also a version of his model is a special case of this. So for each lottery, an agent has a noisy perception of payoffs and probabilities. They maximize expected utility given their posterior about what the lottery actually is. A very simple version of this would be where only the prizes are imperfectly perceived and the probabilities are perfectly perceived. That would actually give you a random expected utility model. This is what Rava you were I think asking about. For each prize, I perceive it imperfectly, and I take an expected utility over these imperfect perceptions. That's like having a random utility of each prize. Okay, let's see. I think I'm gonna skip this and talk a little bit about. So, this is we're putting a lot of demands on our agent now, even though it's an as-if model, because not only the agent has to maximize expected utility, but also has to use this Bayes rule. But we have massive evidence from psychology that says people don't use Bayes rule. There's all sorts of Bayes rate neglect, confirmation bias things. So how come we're allowed to put this into our model? What's going on? Why am I doing this? And so I just want to make a distinction between these kind of two literatures, both in psychology. One talking about how people explicitly fail Bayes rule when they explicitly state their beliefs. And the other one when, these Bayes rule in my model, it's not really my model, but in this Bayes expected utility model, Bayes rule is applied to these internal perceptions. This is not something that the agent is doing consciously. This is some part of the brain that maybe is doing it. And so even though people maybe are bad at explicitly communicating their beliefs and updating their beliefs, internally they may well be pretty good at it. And in fact, this model, as Mike was trying to convince us yesterday, is pretty good at explaining things from psychology like prospect theory. So the difference is that we're sort of doing this at different levels. One is explicit, one is implicit. One is the primitive. These are about probabilities that people state, and Bayes expected utilities at the level of the representation. So that makes me a little bit less troubled about using Bayes rule. The true reason is that, of course, there's infinitely many of these paradoxes, and each of them has kind of a separate model. And so I wouldn't know which model to plug into to Bayes expected utility model instead of Bayes rule. And each of them would lead to a different prediction. And so maybe it's a little bit too early to depart from Bayes rule at this stage. Okay. Yep.
I think in using Bayes rule the way you're using it, you're just hypothesizing that people have somehow learned a pattern of response that is indeed good for them.
Mm-hmm.
It doesn't mean that they are doing the calculation
Yeah.
using Bayes rule to
Yeah.
understand why the habit they've acquired.
Yes, they behave as if they use the Bayes rule, but maybe they don't do it. Yeah. Yep.
In other words, it's a hypothesis about the optimality of their pattern of behavior, which is different from them consciously understanding Bayes rule. We know, of course, most people don't consciously understand Bayes rule because you ask them explicit updating questions.
exactly. Okay, just to sort of sum up, so random utility is sort of a model of random tastes. It's regularity plus some messy axioms. Random expected utility is sort of a model of random risk aversion, regularity plus linearity plus extremeness. Bayesian expected utility, it's sort of a model of random perception. So these are models of what Mike was calling late noise. This is a model of early noise. I didn't mention any axioms because I don't know what they are. There are a lot of papers using this model, but in most of them, the byte comes out of functional form assumptions, and I don't know what the model itself actually excludes. In all of these models, there was an invariance assumption. Either the distribution of utilities is independent of the menu, or the distribution of risk aversion is independent of the menu, or this signal structure is independent of the menu. So if the signal structure is independent of the menu, we sometimes say this is passive learning, as opposed to active learning, when the agent can choose the signal structure. Pay attention to something more than to something else. That's choosing the signal structure. That's what Mike called efficient coding. And there's a whole big literature discussing, what is the appropriate cost function. So you're going to choose beta, but you're going to have to pay something. The attention is not free. What is the cost of attention? The most popular one in the literature is mutual information from information theory. That leads to what Sims calls rational attention, and Lumi is going to give her lecture on that. It's a very tractable model, but actually it has a lot of problems. So for example, in the weight discrimination task, it leads to a stepwise psychometric function. So the agent can perfectly discriminate between things that we know people can't. So many other cost functions have been proposed. This is a very active area. I will not cover it. I will cover sort of a little bit of it in my next lecture, when I discuss a dynamic model, where the agent can decide to gather more information or stop and make a decision early. But just as a sort of a matter of last slide, I know we're out of time, but you can stare at this during the break. This is an example how a model of active learning fails regularity. Thanks very much.